So now let's move on to look at how we can calculate the shape function for some typical finite element that we used in doing FEA. So to start with, let's look at what happened to a triangle finite element as shown here. So we have three nodes in these triangle elements, where I have the displacement on each node being represented by a U1 with a tilde on top. That means that's the displacement at the node, right? And what the shape function want to work out is for an arbitrary point x, y in this element, what will be its relationship for this point uxy with respect to u1, u2, and u3. So that's the idea of the shape function. Okay, now in this course we're gonna assume that everything is gonna be a linear relationship. So we're doing linear finite element analysis. So here we're gonna assume that for any point in this finite element ux, okay, I'll put it as superscript ux, and uy is gonna be some sort of linear function with respect to its coordinate. So ux will something look like alpha 1 plus alpha 2x plus alpha 3y. So if I know the coordinate of this point xy inside this finite element, I can plug in its coordinate x and y and work out the displacement at that point. Of course, in the end, this alpha 1, alpha 2, and alpha 3 will be correlated to u1 and u2 and u3, which will show you how to work that out later. So similarly, uy will also be a linear function of the coordinate. So in this case, let's say this is given by alpha 4 plus alpha 5 x plus alpha 6 y. Now you can see that the equation for ux and uy are symmetrical, right? They are very similar form. So for this lecture, we're going to focus on solving ux first. We'll just solve ux for, as an example, this equation A. So this equation A right. Okay. So how do we solve for A? Now we need some knowledge about the displacement in this finite element. So we basically need three equations to solve for three variables, alpha 1, alpha 2, and alpha 3. But what we do know is the displacements or deformations at nodes 1, 2, and 3. So what are they? They are simply u1x tilde, u2x tilde, u3x tilde, right? And they are related to the coordinate of these 3 points. So the coordinate at these 3 points will simply be x1, y1, x2, y2, and x3, y3. And by knowing that, you can write down the equations as u1x equal to alpha 1 plus alpha 2 x1 plus alpha 3 y1, ux2 equal to alpha 1 plus alpha 2 x2 plus alpha 3 y2. This equal to alpha 1 plus alpha 2 x2 x3 plus alpha 3 y3. Right? So now we have the equations that allow us to solve for x1, x2, and x3. Now, for this course, that's actually not gonna be meaningful if we go through the whole mathematical derivation of how we solve this, right? You can either do it with substitution, or you can also do it with elimination. But the key idea is here to solve these three equations for alpha 1, alpha 2, and alpha 3. Now we're just going to show you the final solution and discuss what the meaning of that solution is. Okay. Alright. Now the first thing we need is the value of the determinant for the system of equations of. Now, if you know the definition of determinant, in this case delta, determinant will be given by 1, 1, 1, x1, x2, x3. Now notice x1, x2, x3 are the known value because they are the coordinate. They are not the unknown variable in this case. So we have y1, y2, and y3. Okay, now the idea is to work out what do we want to work out? We want to work out the expression so work out the values of alpha 1, alpha 2, alpha 3, and these are given in terms of x1, x2, x3, y1, y2, and y3. So we'll be able to work out these three alpha value based on the coordinates, and then we substitute alphas back into equation A, which is this guy here, so we can get the relationship of ux, so the displacement of an arbitrary point in the element on the x directions as a function of this guy. Okay, so that's the whole mathematical mechanism to work this out, which we're not gonna go into the detail of all the math of how we do it. But if you do solve it, you can find out ux can be written as following: 1/2 delta times A1 plus B1x plus C1y. So you see there's the coordinate x and y, the position of that points in the element we are interested in, times U1x, right? The x displacement at node 1. And similarly, we'll have A2 plus B2x plus C2y times U2x plus A3 plus B3x plus C3y times U3x. Now this probably doesn't make sense at the moment, but basically all these A, B, and C are coefficients. So A, B, and C are coefficients that depends on x1, x2, x3, y1, y2, and y3. Right, so using the x1, x2, x3, y1, y2, and y3, we can work out the a, b, c values. So for example, a1 is equal to x2, y3 minus x3, y2. b1 equal to y2 minus y3. C1 equal to x3 minus x2. Now in the lecture notes, you will see there's a sentence that says A2 and A3, for example, can be worked out from the cyclic permutation of the subscript. Now you'll say, what's a cyclic permutation of the subscript? This is a shorthand notation for us to avoid writing a lot of similar equations repetitively. So if you look at a cyclic permutation, the easiest way to think about it is to write the three numbers 1, 2, 3 in a circle, and then you move forward by going clockwise direction. So how does that work? If I want to write A2, for example, from A1 using this cyclic permutation, we'll still have some sort of xy minus xy. Now the subscript of 2, the subscript of this equation in here is 2, right? So 2 goes to what? 3 in this cyclic permutation. So here 2 goes to 3, 3 goes to 1 in this direction. So 3 goes to 1 and 2 goes to 3. So that's how you will work out the value of A2, so on and so forth. So now we have these solve this sort of the shape function, right? We have solved for this shape function in this form, okay? Right? So now we can simplify it, because eventually we know the n, the shape function, which we talked about in previous video, will be a matrix, right? But this doesn't look anything like a matrix. This is basically a long equations. So how do we do that? Let's just rub this bit out, and then we can sort of show the important bit. So what we can write is, say, this ux is 1/2 delta, or we can even ignore this delta. We say this bit times 1/2 delta give me a function that is n1, right? So this is an n1 value times u1 of x. Right, this simplify a little bit, so you'll know that this n1 is all of this guy. So this is n1, and similarly you can write this as n2 times u2x, and this is n3 times u3x, where in here n(i) equal to what? 1/2 delta times ai plus bix times ciy, where I equal to 1, 2, and 3. I think this simplifies things a little bit. Right? Similarly, we can write u of y. Well, we didn't solve it, but by the analysis or energy of the equation, the form of the equations, we can write this down as n2, still n1 times u1y plus n2 times u2y plus n3 times u3y, right? So now we have two equations that relates ux, uy to u1x tilde, u1y tilde, so on and so forth. So what do we actually have? If we now write this as a matrix equation, or in the form of matrix times vector give back another vector, we have on the left hand side ux, uy. So that's the vector we want to get, and the displacement in an arbitrary point inside the triangular matrix element, or triangular finite element, sorry. And on here, what do we have? We have the displacement at each individual node. So we can write this as a column vector, which will be u1x tilde u1 or u1 y tilde. So this, so we got this, and similarly u2x tilde u2y tilde u3x tilde and u3y tilde. So this is a 6x1 column vector, and this is a 2x1 column vector. So here will be our shape function, or the shape function matrix, and this is going to be a 2x6 matrix. Now what will be the elements in this 2x6 matrix? Right, this is our matrix N. With bold letters, so this is the N matrix. We will have, say, ux is gonna be only depend on u1x tilde. So here will be n1, right? ux in this column, you need to have this row transpose and times the the column vectors. So Ux does not depend on U1y, as you can see about here. So the second element will be 0. Now Ux does depend on the third element, U2 x tilde, and the coefficient is n2. So this element will be n2. And then similarly will be 0, n3, and 0. Now you can also work out the value for the next row, which will be 0, and 1, 0, and 2, 0, and 3. So this bit, right, at the end, this matrix is gonna be our shape function for a triangular finite element. Okay, so now we are done for this part.